So now that we've seen how you calculate area and polar coordinates, let's look at an example. Let's find the area inside the cardioid, r equals 1 plus sine theta. So we're not given any limits here because remember the cardioid is a closed curve, so we just need to make sure that we draw the entirety of that cardioid once and only once. So let's think about the picture. Now we know that that's the cardioid. We might not remember the orientation. So let's just think about where we're at each of the major angles there. So when we start off, theta equals 0, sine is 0 plus 1. So you're out here at an r of 1 at that point. When you move to theta over 2, it's 1 plus 1, or 2. And at pi, you're back to 1. And at 3 pi over 2, that's 1 minus 1, or 0. So that reminds me then, okay, that I don't have to do my full analysis again because I remember the general shape of that. I just had to remember the orientation, so I know it's going to spiral out kind of symmetrically that way and that way. So there's our cardioid. And in the process of doing that, that also reminds me that I have to go from 0 to 2 pi, or an interval of 2 pi, to get the whole thing. Now, I could start wherever I wanted and end wherever I want because wherever I start, I just have to go a length of 2 pi, and I will have drawn that exactly one time. So it's kind of up to us what our limits are gonna be. I guess the simplest thing would be to just start at 0. And I want to emphasize that when you're thinking about area, it's really those sectors, right? So when I shade in polar, just to remind myself of that, I always shade with these radii coming out from the origin. So, remember, area is the integral from alpha to beta of 1/2 our function squared, right? It's a little bit different than Cartesian. And so in this one, so long as we just go sweep around exactly once, we're good. So I'm going to start at 0 and go all the way around to 2 pi. That'll draw it exactly once. So 1/2 the function squared. In this case, we're on the curve 1 plus sine theta. Now, one thing you'll see a lot is because there's a half in here, if you can take advantage of symmetry, and this thing does have symmetry, you could take half of that integral and double it, and that would get rid of your fraction that you have in there. So a lot of times if you're looking at solutions, you'll see them using symmetry to eliminate that half. I thought for a first example I wouldn't jump into symmetry, but we could have gone from negative pi over 2 to pi over 2 and doubled it. And that would have got rid of the half. But let's just stick with this setup. I will take the half outside, though. No need to have that floating around in there. And then I'll multiply out. Now, because a lot of our polar curves involve sines and cosines, and because area involves squaring, you're going to have a lot of sine squareds and cosine squareds. So this will get us thinking about those trig identities again. So remember, to integrate sine squared, I'm going to have to use the identity. Sine squared is 1/2 minus 1/2 cosine 2 theta. That gets me down to first degree there. 1 plus 1/2 is 3/2. So I'm not going to write that in a separate step. So I've got 3 halves. When I integrate that, that's 3 halves theta plus, I guess that's going to be minus, right? So I'll say negative 2 cosine theta. I integrate that. And then here we're going to divide by 2 when we integrate, so minus 1/4 sine 2 theta. 0 to 2 pi. Now we just evaluate. 2 pi into there would be 3 pi. Cosine of 2 pi is 1, so that's minus 2. Sine of 2 pi is 0, so plus 0. And then 0 into there is 0. Cosine of 0 is 1, so minus 2. And sine of 0 is 0. Those 2's cancel. So we're just left with 3 pi times the half, or 3 pi over 2. So take advantage of symmetry if you want. I decided not to here. And actually, it works out pretty good because without the symmetry, notice that you get really nice values when it came to time to evaluate these, as opposed to using negative pi over 2 and pi over 2. So, you know, it kind of depends. The symmetry doesn't always make it easier, but it could. It at least gets rid of the half. And remember your identities. You'll be using a lot of the 1/2 minus 1/2 cosine 2 theta. Or remember, if this is cosine squared, then it's 1/2 plus 1/2 cosine 2 theta. But either way, it's, you'll be using those a lot because of the fact that you square in the formula.